Today we'll talk about the interfaces. So the acoustic interfaces are the media boundary when two or more than two media join with each other. So the joining line of the media is called acoustic interface, which is also called reflector because sound waves are reflecting from the interfaces. The strength of the reflector or the interface depends upon the acoustic impedance mismatch. So now the question is that what is acoustic impedance mismatch or what is acoustic impedance? So by definition, the acoustic impedance is the ease with which sound wave can form in a medium. Actually, if you search for the definition of impedance in the dictionary, so you will see that impedance means resistance, but here I will tell you that it's neither resistance nor ease, but it's actually the overall characteristics of the medium or the molecular arrangement. Because acoustic impedance is represented with English letter Z, and it's a product of speed of sound and density of the medium. So here, if you look the for the density of the medium. So the density of the medium depends upon the molecular arrangement. If the molecule of the medium are densely arranged, compactly arranged, then there are a number of molecules in a small volume, then you will say that the medium is denser. But if the molecule are loosely bounded, and they are far apart from each other, and in a unit volume there are less number of molecules, then you can say that the medium is less dense. So it's mean the density of the medium depends upon the molecular arrangement or the compactness of the molecule. So this is the ultimately you can say that this is the molecular arrangement. Now if we come across the speed of sound, so you know that the speed of sound depends upon the molecular arrangement or the medium again, because the different medium have different molecular arrangement. That's why different medium have different speed of sound as well. You know that the speed of sound in soft tissue is 1540 meter per second. The speed of sound in bone is 4000 meter per second. The speed of sound in air is 330 meter per second. So that's why you can say that the speed of sound in different medium is different, because the molecular arrangement of the media are different. And you also know that the speed of sound depends upon the density of the medium again, and you know that it's also depends upon the elasticity of the medium or stiffness of the medium. So the stiffness of the medium, elasticity of the medium, density of the medium, all these things are related to the molecular arrangement. So if we summarize the acoustic impedance, then we will say that the overall characteristics of the medium are the molecular arrangement of the medium. So this exposition is actually enough for the acoustic impedance, and by this way, you can say that the X-ray, the CT scan, that depends upon only one parameter, and that is density. But ultrasound depends upon two parameter. One is density, and the other one is the speed of sound. And in some cases, the CT scan or X-ray image differ from ultrasound image. If you compare the X-ray image for the abdomen, and you look for the abdominal ultrasound, so if whenever there are some gases in the intestine, they will appear on X-ray as black regions, because the X-ray can easily pass through that air, and the film can easily be exposed, and that region will appear on the X-ray film as black area. Similar in the CT image as well. But if you look to the ultrasound image, then you will realize that air appear a highly echogenic, bright structure and the ultrasound image. So this is the main difference between the CT, X-ray, and ultrasound image. Because ultrasound rely on two parameter. These are speed of sound and the density of the medium. Because the acoustic impedance of different medium is different, if they have different speed of sound and a different density. Now there some the acoustic impedance of a few medium is shown over here for the sake of understanding. So you can say that the acoustic impedance of the air is 0.004, that of soft tissue is 1.63, bone is 7.8, and crystal is 29. So this is just for the sake of understanding, right? Just assume that on one side there is air, and on the other side there is soft tissue. So that the interface in between these two medium will be formed. How strong will it be? So we can calculate the strength of that reflector if we know the acoustic impedance of the two medium. So how will it be calculated? We can calculate this acoustic impedance with the help of intensity reflection coefficient, right? So the intensity reflection coefficient is can be defined as the percentage of uh, sound wave that can be reflected from a specular interface or a large interface, because there are two main kinds of interfaces. One is called specular interface and the other one is scatter. So the amount or the percentage of sound wave that can be reflected from a specular reflector is called the acoustic impedance. Intensity reflection coefficient, sorry. So the intensity reflection coefficient can mathematically be expressed as the difference in the acoustic impedance of the two medium. If the acoustic impedance of the medium 2 is Z2 and the acoustic impedance of the medium 1 is Z1, then the difference between these two medium will represent its strength, right? But if we are going to calculate the intensity reflection coefficient, then we will have a specific formula for it. And the formula is that Z2 minus Z1 divided by Z2 plus Z1 whole square, right? Now, here a question arises. If it is the difference in between the acoustic impedance of the two medium, then why is it long formula? Why is it not the simple difference between the two medium? For example, if we calculate the difference in the acoustic impedance of the two medium, won't it be enough for the intensity reflection coefficient? So definitely that will be enough. But we are going to we don't know about the Z2 or Z1 value, whether Z2 are greater or Z1 is greater. So if in this formula, just assume that Z2 is smaller than Z2 is smaller than Z1. For example, Z2 is 5 and Z1 is 10. So what will be the result? The result will be negative number, right? Minus 5. If Z2 is 10 and Z1 is 5, then we'll have positive number, and that will be plus 5. So if we get a negative number, we are not interested in that negative number. For the IRC, we want to have a positive number. So for that purpose, if this minus 5 is squared, so it will become plus 25. But the same way, and simultaneously, we have also squared the denominator, which is z2 plus z1. So if both the sides, numerator and denominator, both of them are squared, then there will be no difference on the overall result. So that's why it was squared. And why is it divided by total acoustic impedance? For example, Z2 plus Z1. So because we are going to take the value from 0 to 1 and decimal point, and that will be important for the percentage, because if we simply multiply it with 100, then you will get percentage. For example, we have a number of this IRC, and that is point zero 5, then we can easily multiply it with 100 and we'll get the percentage. So that will become a 5%. So this is the formula. You will have to learn it by heart, and the time of for this session will only be 10 minutes more. So we'll terminate this lecture soon and we'll resume it, right? So this was all about the intensity reflection coefficient, and you should know about the intensity reflection coefficient, and you will have to solve a little bit numerical on this formula, right? And I will give you about 2 to 3 assignments to clearly understand this formula, right? One assignment is for you is that you'll have to calculate the acoustic intensity reflection coefficient if the interface is formed in between the air and the soft tissue. And the other assignment should be like this: if the interface is formed in between the transducer crystal and the soft tissue, so how strong will the interface be and what will be the IRC from that reflector? And that is too important as well. If you place the transducer on the soft tissue, then the transducer crystal has acoustic impedance of 29 and the soft tissue of 1.63. So it's mean if you calculate the IRC between the transducer crystal and the soft tissue, you will get a very huge percentage of sound wave that can be reflected from this very first interface. So we'll have a high IRC. But this time you are interested in ITC. What is ITC? The amount of the percentage of sound wave that can be transmitted through a specular interface. Whenever there is an interface and sound waves are hitting against it, so some of the sound waves will be reflected, but some of the sound waves will succeed to pass through that reflector. So the percentage of sound wave that can be passed through a specular reflector is called intensity transmission coefficient. So if we place the transducer on the soft tissue, then we are interested in the ITC, intensity transmission coefficient. We are interested in the fact that sound wave can transmit into the body. The sound wave propagate inside the body and bring information from the body. But if sound waves are reflected from the superficial reflector, the reflector which is found in between the soft tissue and the transducer crystal, so most of the sound wave will not be succeeded to enter the body, and those sound waves will not be useful for us because they can't bring useful information. But you can say that these sound waves are lost. So for that purpose, we are interested to improve the ITC and reduce the IRC, and that's why we are going to use acoustic gel. So what will be the acoustic impedance of the acoustic gel? So the impedance of the acoustic gel will be in between the soft tissue and the transducer crystal. Then you will have most probably an MCQs. You will be given values. For example, if the acoustic impedance of the transducer crystal is 10, this is just assumption. Assume that the acoustic impedance of the transducer crystal is 10 and the acoustic impedance of the soft tissue is, for example, 1. So what could be the acoustic impedance of the gel? And you will be given options. For example, the acoustic impedance of the gel could be 0. The acoustic impedance of the gel could be 5. The acoustic impedance of the gel could be 15. The acoustic impedance of the gel could be 20. So what will be the correct option? Can anyone tell me? So I will tell you that the correct option of the acoustic impedance of the gel will be 5. That could be in between the transducer crystal and the soft tissue because they act as a mediator. They act to minimize the acoustic impedance, and they act to minimize the acoustic impedance mismatch. They uh, uh, with the medium to reduce the cost complex mistakes, to reduce the IRC and to improve the transmission of sound. Now we are going towards the interface. When there are two primary one is so what is the specular interface? If the size of the interface is greater than the wavelength of the incident sound wave, then it is called specular interface. So here in this example, the size of the reflector is from here to here. This is large enough as compared to the wavelength of the incident sound waves. So according to the definition, this is a specular interface. Once again, you should know about the definition of the specular interface. So, if the size of the interface is substantially greater than the size of the wavelength of the incident sound wave, then that will be specular interface. And you can say the reflection from the specular interface will be specular reflection, and specular reflection will always be angle dependent. If we have normal incidence, by normal incidence you mean that if the sound waves are striking the interface at orthogonally at 90-degree, then they will reflect back at the same angle. They will be received by the transducer and the image of the structure will be formed. So here we are going to calculate all the angles from an imaginary line that could be drawn perpendicular to the interface. And why is it so? Because we are following most of the experiments which were already done on the light waves, because in most of the characteristics sound waves exhibit the same characteristics as that of the light wave. That's why we are drawing a perpendicular line, which you can see over here in this image, and the form of a yellow line or dotted line. So all the angles should be measured with this imaginary line. So the angle of incidence will be this one, right? The angle of reflection will be this one, right? The angle of transmission will be this one. So all the angles will be zero if there is normal incidence. If the incidence is normal, the sound waves are striking the reflector at 90-degree, then or you can say that the angle of incidence, if the angle of incidence is zero, because here the imaginary line will be like this. So the angle of incidence will be zero, the angle of reflection will be zero, the angle of transmission will also be zero. So all the angle will remain the same if there is normal incidence. But if there is oblique incidence, just for example, like over here, so this is oblique incidence. So in the case of oblique incidence, the angle of reflection will be equal to the angle of transmission, and similarly to the angle of reflection. So that in this case, how much the strength of the reflector may be, but it will not appear on the ultrasound screen because the transducer is placed over here. The sound waves were reflected in this direction. They didn't come back towards the transducer. So how will it be depicted? How will its image be formed? So the image of this structure will not be formed because these sound waves are moving in other direction. They are hovering here and there. They are not coming back towards the transducer. That's why, irrespective of the strength of the reflector, it will not appear on the screen because these sound waves are not coming back towards the reflector. And then we can say that the angle of transmission, which depends upon the refraction, and well, soon we'll discuss about the refraction. But here in the case of the scatter, this according to the definition, if the size of the reflector is small enough, then the wavelength of the incident sound wave is called scatter. But I think we'll have to arrange another session for the scatter because this session is almost to be over now. So thank you very much, and see you in just now.